So this video is a brief description of the propagation of light in a medium from the atomic scale point of view, which is the basis of Snell's law and the law of reflection, and shows why some mediums are transparent and some have certain colors, and why some are reflecting like a mirror or absorbing. So after the development of Maxwell's electromagnetic theory, it was shown theoretically that an oscillating electric dipole emits electromagnetic waves. So this image here is a 3D view of the radiation pattern of a Hertzian dipole, which is an idealized infinitesimal dipole. So as you can see, the pattern is the typical donut-shaped pattern of dipole radiation. And this image here shows a horizontal cross-section of this radiation, and this is a vertical cross-section. So in the far-field region at sufficiently large distances from the dipole, the radiation can be described as a plane wave, which means that the electromagnetic waves propagating outward become similar to plane waves, where the wavefronts are planar and the electric and magnetic fields are perpendicular to each other and to the direction of propagation. So in 1878, Henrik Lorentz proposed the idea of considering the atom itself as an oscillating dipole, and this is known as the Lorentz oscillator model. And this is because by that time it was already discovered that atoms emit and absorb electromagnetic waves at certain discrete frequencies, as was observed in the absorption and emission spectra of atoms. And so Lorentz proposed this model to explain this phenomena. So in Lorentz oscillator model, each electron in the atom is assumed to be held to the nucleus by a spring. And this spring represents the restoring force for small displacements from equilibrium. So the negatively charged electron and the positive nucleus form an electric dipole. And because of the nucleus' heavier mass, it can be assumed to be stationary during oscillation while the electron oscillates back and forth. So as we know, for a mass spring system, and you can find more about this in the oscillatory motion chapter in my book Principles of Mechanics, which you can find in the bio, and it is available for free. So there you can see that the natural resonant frequency omega naught of a mass spring system is given by this equation, where k is the spring constant and m is the mass of the block. So in a similar way, Lorentz showed that the natural resonant frequency of the atom or dipole is given by this equation, where mu is the reduced mass of the system and Ks is the spring constant that represents the magnitude of the restoring force in the atom, and is chosen in a way that omega naught here coincides with one of the natural frequencies of the atom. So an atom has many transition frequencies, as was revealed in the absorption and emission spectra. So there are several natural resonant frequencies in an atom, and so we suppose that there are several dipoles within every atom to account for this, each with its own natural resonant frequency. So as the electron oscillates, it produces a time-varying dipole, as you can see here, which adds to any permanent dipole already existing in the atom. So this figure here shows a classical oscillating dipole consisting of a heavy positive charge and a lighter negative charge that are bound together by a spring. So xt here is the time-dependent displacement of the negative charge from its equilibrium position. So this is the displacement here, and this is the equilibrium position, and this generates a time-dependent dipole moment. So when light of a frequency omega is incident on an atom, the mechanism of interaction is that the AC electric field E of this electromagnetic wave will drive oscillations of the electron in the atom at the same frequency omega of the wave. In a similar way to forced vibrations in a mass spring system, which you can find more about in the chapter of oscillatory motion in the book in the bio. So just as a forced vibrating mass spring system, if the frequency of this wave omega coincides with one of the natural resonant frequencies of the atom, the resonance occurs, resulting in large amplitude oscillations of the atom, which is behaving like a dipole, and transferring the energy from the wave to the atom. And so at resonance, the atom will absorb energy from the wave. And so the condition for resonance or absorption is that the frequency of the wave omega is equal to one of the natural frequencies of the atom. So this is the condition for resonance or absorption, when the frequency of the coming electromagnetic wave is equal to one of the natural frequencies of the atom. So the transmission of light in a certain medium is related to absorption, because only the frequencies of light that are not absorbed in the medium, which means frequencies that do not coincide with any of the atom's natural resonant frequencies, will be transmitted through the medium. So such frequencies will pass through the medium. And so selective absorption of certain frequencies of light in the medium is responsible for the coloration of many materials. For example, a ruby is red because it absorbs blue and green light, but not red. So once an atom in the medium is promoted to an excited state through absorption, it can de-excite through several mechanisms, such as through the process of spontaneous emission known as luminescence, or through dissipating the excitation energy as heat, which sometimes occurs before the radiative free emission process. And so the efficiency of luminescence depends on the dynamics of the different de-excitation mechanisms in the atom and does not always accompany absorption. So once light is absorbed at one of these natural resonant frequencies of the atoms are excited and then de-excited either through luminescence or through other mechanisms such as dissipation by heat. So if the incoming light has a frequency that coincides with one of the natural frequencies of the atom, a resonance occurs, then the atom absorbs energy from the wave, then light of the resonant frequency will be attenuated as it progresses through the medium. So now let's suppose that the frequency of the coming electromagnetic wave does not coincide with any of the natural resonant frequencies of the atom. Then the atom will not absorb the coming light, and instead the wave will drive non-resonant oscillations of the atom at the same frequency of the coming wave, and the medium of such atoms will be transparent to the coming wave of this frequency. So in this case, the oscillations of the bound electrons in the atom will follow that of a driving wave but with a phase lag. And so the oscillating dipole or atom will re-radiate an electromagnetic wave at the same frequency of the coming wave. So these atoms here will oscillate and radiate electromagnetic waves at the same frequency of this driving wave. But the phase lag of the oscillations will retard the propagation of the wavefront, which results in the propagation velocity of the wave to be smaller in the medium than in free space. And this slowing down of the wave in the medium is characterized by the refractive index n. So the refractive index of a certain medium is given by c over v, where c is the speed of light in vacuum and v is the speed of light in the medium. So for vacuum and also for air, v is equal to c, and so n is equal to 1. But for glass, for example, v is less than c and n is equal to 1.5. So the non-resonant interactions between the atoms and the wave can be viewed as repeated scattering processes, where each atom can be considered as a Huygens point source and where the scattering is coherent and elastic. So the scattered light from the atoms interferes constructively in the forward direction and destructively in all other directions, making the wavefront to continue to propagate in the same direction in the medium. But because each scattering process introduces a phase lag, the wavefront propagates with less velocity, and this reduction of velocity also results in the bending of light rays at the interface between two mediums for oblique incidence as described by Snell's law of refraction, such as when light travels from air to glass. So note here also that as the wave travels from one medium to the other, its frequency does not change. And this is because the speed of the wave is related to its frequency and wavelength through this relation. And because both the wavelength and the speed of the wave changes as the wave travels from one medium to the other, then the frequency of the wave will remain the same because it is equal to v over lambda. And because, as mentioned before, the energy of the wave is related to its frequency, then the energy of the wave does not change as it travels from one medium to the next. And this means that the blue light will remain blue as it travels from air to glass, for example, and the red light will remain red. Also note here that we assume that the force exerted by the electric field of the wave is small compared to the binding forces that hold the electrons to the nucleus. But if, for example, powerful laser beams are used, then this is considered in the field of nonlinear optics. So far we have considered the oscillations of bound electrons in the atom. But other types of oscillating dipoles, not originating from the bound electrons in an atom, can also be present in the medium. For example, an ionic medium contains oppositely charged ions, and when these ions, which are atoms with a positive or negative charge, oscillate around their equilibrium positions, they will produce oscillating dipole moments with certain resonant frequencies, and such oscillations are associated with lattice vibrations and occur in the infrared spectral region. So another type of a vibrational oscillator is a polar molecule as shown here, which consists of two oppositely charged atoms. So the charged atoms can oscillate around their equilibrium positions and produce an oscillating electric dipole that is analog to the oscillating dipole due to the bound electrons in an atom. But because of the larger reduced mass of the oscillator in the case of a polar molecule, as compared to the bound electrons' dipole oscillator reduced mass, such vibrational molecular oscillators have absorption lines at lower frequencies in the infrared region, as opposed to the case of the bound electron dipole oscillators, which usually have natural resonant frequencies in the visible and ultraviolet spectral regions. So the models used to describe the interaction of electromagnetic waves with matter can be classified into three general categories: classical, semi-classical, and fully quantum. So in the classical approach, as in Lorentz oscillator model, both the light and the medium are treated using classical physics, where the light is treated as an electromagnetic wave and the atoms as classical dipole oscillators. And in the semi-classical model, the light is treated as a classical electromagnetic wave, while the atoms are treated using quantum mechanics, where the energy levels of the atom are quantized, which means the atoms have discrete quantum levels. So according to quantum theory, when there is absorption of light by an atom, what happens is that the atom is excited and then returns to its ground state, either through a series of radiationless transitions converting the energy of the incoming wave into heat, or through luminescence by re-emitting a photon. And finally, in the fully quantum model, both the light and the atoms are treated according to quantum mechanics, and the light is considered as a beam of photons. So the oscillating dipole model described in this video, due to bound electrons either in the atom or in vibrational dipole oscillators in an ionic medium or polar molecules, are all examples of bound oscillators where the electrons are not free. But in metals and doped semiconductors, a significant number of electrons are free and not bound to any atoms but are free. And so such electrons in a metal or semiconductor do not experience a restoring force when displaced from equilibrium. So the application of the Lorentz dipole oscillator model to the oscillations of free electrons in a metal is known as the Drude-Lorentz model, where because there is no restoring force, the spring constant Ks is zero, which implies that the natural resonant frequency is also equal to zero. So the Drude-Lorentz model shows that the free electron gas reflects all frequencies up to a certain frequency known as the plasma frequency omega p, which is the natural resonant frequency of the collective electron gas as a whole. So the whole electron gas in the metal will oscillate back and forth, and omega p typically lies in the ultraviolet region. So the reflection of all frequencies of light by the free electron gas up to the plasma frequency, which is in the UV region, is the basis of the law of reflection of light. So a mirror is made of a thin layer of metal, such as aluminum or silver, that is usually coated on a glass substrate. And all frequencies up to the plasma frequency are reflected by the mirror. So thank you for watching, and I hope this video helped you in grasping the underlying mechanism for reflection and refraction.